Okay, so yeah, let's get started. How's everyone doing? Good. So I'm still recovering from a cold, but so hopefully I can keep talking. Um, if I talk for long, sometimes I start coughing. So that's one thing I need to watch out for. But if I feel that way, then I'll stop after some time, like after an hour or so. But if I feel I can continue, I'll continue. So welcome to lecture 5, recommender systems. Um, let's go through some logistics and so it's recording. Yeah. Can also answer any questions you guys have. So programming 2 is due this Sunday. There are 2 parts to this, part 1 and part 2. So this is easy. Oh, that was not expected. Okay, this is easy and this is not easy. So, if you finish this and you're happy, then this is coming up. Just make sure you allocate time so that you finish both part 1 and part 2. So part 2 was also part of the original upload I put in, but I noticed there is some things that may need working on the framework that's being used there, MXNet, and if everything's updated there. So I'm just making sure it'll be updated, and then I'll post the part 2 as well. Meanwhile, you can work on part 1 and get a feel for it and make sure you're up to speed. Um, so if we didn't have any deep learning, programming 2 will finish our recommender systems course because it involves SVD, it involves all kinds of thumb rules that people used to use for recommendations. It involves matrix factorization. It involves stochastic gradient descent. It involves regularization. So it's pretty comprehensive. So in the pre-deep learning era, people will be like, oh yeah, this is 80% of recommender systems. And then, you can put it either way. It's 80% of what you can learn from a course. And then you have 80% more to learn in person as you work on data in a company, right? But with the advent of deep learning, obviously there is so much more you can do. And so we'll probably have 1 or 2 more programming assignments um, to focus on deep learning as well. And there's also your project. So the project is also going to, I think we'll have the proposal. Yeah, so I should have, let me make sure it's updated here. Let me pause the recording. Okay. So yeah, so programming 2 is due this Sunday. So hopefully that's enough time, but just make sure you allocate enough time for both the parts. And this is a really critical programming assignment. Like if you are good with this, you understand the nitty-gritties of baseline recommenders, of SVD-based recommendation, matrix factorization-based recommendation, usage of SGD, and it's really amazing. It gives you a lot of foundation. And then when you launch into a project that might be coming up, you'll be more comfortable, handling the nitty-gritties there as well. Okay. Yeah, so again, cannot emphasize enough, please spend good amount of time on this programming assignment so you're in a good place for it. Yes, so we discussed this as well. Any questions on grading? Anyone? So one thing I think that came up somewhere is, you know, the grading is like, you have conceptual programming and project, right? So these are the 3 different aspects. So the project obviously will have a significant weightage, like 30 to 40% of your weightage, right? There's no final exam in summer quarter. You don't have final exam. There's no midterm as well. So a lot of your focus will go into the project. Programming is going to also take a significant weightage, like 40%, and conceptual is going to be 20%. So that's your 20, 40, 40 split. between programming, conceptual, and project. Now for programming itself, programming 2 is going to take more weightage than programming 1, right? So just FYI, programming 2 has more weightage. But if you look at the number of points that's been assigned to a programming assignment, don't worry about that. This is the actual weightage between conceptual programming and project in terms of your grade, right? So even if your project says 10 points, that's 10 points is worth 40%. So don't worry about what the points is saying there. The points is just saying how well you've done there, but it finally will be converted to a percentage, which should be based on this. Yeah. Any other questions? Okay. Okay, so let's go back to where we left off before our guest lecture last week. There's some limitations of SVD. We spoke about SVD and dimensionality reduction. So there are some limitations of SVD. So for example, PCA is based on SVD for dimensionality reduction, but PCA is not robust outliers. SVD is nice baseline. However, it is very specific. It requires the factors UV to be orthogonal. Just to jog your memory, SVD is you divide into U, and then you have sigma, and then you have so this is U sigma V transpose, and this is your X, right? So this is SVD, right? So for any matrix, any data matrix X, you can compute the SVD, right? So these are orthogonal factors. So that's nice, but and that's the fact that it's orthogonal gets used in PCA, right? If it's not orthogonal, you're not going to get these dimensions along which there's maximum variance, and then the next dimension along which there's more variance. So your data can be divided in these dimensions because of SVD giving you orthogonal factors, which then gets used in PCA. So you can understand your data better because of the orthogonality. But okay, so that's good for PCA, but then if you want to do other things, then that can become a limitation. Right? Orthogonality can become a limitation, right? And it's not flexible to regularization, requires behavioral data, cannot handle hybrid formulations. And also there's one more limitation here. Any guesses? Another limitation. Can't work on an incomplete matrix. So you cannot give a matrix that's incomplete, some question marks or NANs, and say compute this video. It's like, no, you have to have every single entry being mapped out, which means you're making assumptions and making assumptions on data that you don't know, right? And sometimes that that may not work in your favor. And especially in recommender systems, that would mean you're making huge assumptions because there's a lot that you don't know. Only a few products gets purchased by any given customer. An average customer might purchase 100 or fewer products, in many years, whereas there is like hundreds of thousands of products. So that whole rest of hundreds of thousands of products, those entries become question marks, right? So if you look at this customer product purchase matrix, there's going to be a huge number of question marks. So there's more unknowns in that matrix than knowns. So you can't be making assumptions on the unknowns and expect to get a good recommendation or good factorization or good representation. So that's where that's another limitation of SVD. Then there is matrix factorization. We spoke about this as well. which takes care of a couple of the limitations, which is U and V don't have to be orthogonal. You can, just have it be anything, and you can also impose certain constraints on U and V, but it's your choice. You can impose it as you wish. So this makes it more flexible on U and V than SVD. So this, this flexibility has led to many other factorizations. We'll not look into those, but you can look it up. There is like CCA, and there is like other kinds of factorizations as well that are really helpful. There's also non-negative matrix factorization, so where certain factors are non-negative. And this is important when you want your data is non-negative. So it doesn't make sense for your factors to be non-negative if you want to interpret them. So sometimes for the sake of interpretability, you want non-negativity in the data, in the factors themselves. But PCA, SVD is not going to give you guarantee of non-negativity. Even if you have non-negative entries, SVD can give you negative entries in the factors. But when you collapse it, it'll become non-negative, obviously, because X is non-negative. But so these are some subtleties in the factorization process itself that you get interesting factorizations when you look at matrix factorization as compared to SVD. So NMF, CCA, there's also LCA, and there's many other factorizations. So we'll not look into many of this because it's not relevant for recommendation systems, but just wanted to mention that. But matrix factorization is very relevant. It's also relevant because it helps, this kind of factorization helps you with scaling, scaling the training process, scaling the learning of U and V. So when you want to use, let's say you have, let's look at an example where you have 1 million customers. So 1 million customers and 100K products. So that's, how much is this? That's like 100 million possible entries, right? But you might only have like you might only know like 1% of this matrix, right? So you are still computing a U and V that is substantially big, maybe not as big. Let's say your U is 1 million by, let's say you're looking at 100, let's say you're looking at 1,000 factors, and then V is going to be 1,000 by, any guesses? What is this number? You can just
100K.
100K. Yep. Okay, so so we are looking at learning at least on the order of, wow, that's a lot. That's interesting. Did I miss something here? Oh, this is not right. This is 100K million. So that's actually 100 billion, right? So I'm mistaken here. That's what I was like, whoa, this seems a small number. Okay, so this is actually a crazy number. So this is 100 billion possible entries, which you probably don't know at all. Like, I mean, you probably know, maybe this is also exaggerated. So you might only know like 0.01% of this number in practice, based on how many customers have purchased how many products, right? So, but what are you learning? You're learning U and V. So what is the order of the number of parameters you're learning? just look at this and this. What's the order? So clearly U has more parameters than V, right? So the total number of parameters is how many you have in U plus how many you have in V. But since U has more parameters than V, the order is the order of U. And its order, this times this, right? Which is 1 billion. So let's look at this. You have 1 million customers, 100,000 products. That gives you 100 billion possible entries in a data matrix, right? And you have a U that's of 1 million by 1,000, which is 1 billion entries. Maybe for that reason, you might even chop it off to 100 factors to keep it 100 million entries, and that makes a difference sometimes. But let's say you still kept it at 1,000. The order of the number of parameters is 1 billion. So you're learning 1 billion parameters so that you can predict up to 100 billion possible entries. Once you know U and V, you can predict 100 billion possible entries. Do you guys see that? Even if you only knew 0.01% of that. So this is not coming from matrix factorization, it's coming from matrix completion, which is what we'll cover in the next slide. But this is a good example for matrix completion as well. But let's look into that in a bit. So this is in reality, you will only know 0.01% or 0.1% of the matrix. Yeah, so 0.01% is 10 to the negative 4. So that's, yeah, it's like 100 million. Okay, so if you knew 100 million entries and you learn a U and V from that using matrix completion, you can predict 100 billion possible entries. So from just 100 million data points, you can predict 100 billion possible outputs. And that is a power of matrix factorization with completion. So I'm saying with completion because here, even matrix factorization, you assume X is kind of complete. So it's a complete matrix. But in matrix completion, you remove that assumption. You're saying, let X be incomplete. That's okay. We'll only use the entries that we know. We'll not make assumptions about entries that we don't know. So it's a true, with no assumptions on data-based model that allows you to use a few data points to extrapolate to as many predictions as you can make, especially in the context of recommendation systems. Okay. Any questions on this? The math we are looking at here. I mean, we'll look at this again when we get to matrix completion. So I want to make sure that this is really clear in our head. Okay. We looked at, yeah, so missing ratings and matrix completion. Yeah, so this is what we're talking about, right? In practice, you'll never have a matrix X that's complete. So X is usually going to be incomplete, right? Like, one customer. It's acting strangely today. So one customer might rate or purchase. Oh, some strange behavior. I think, I don't know why it's so sensitive. Maybe I'll just prop it up. So my rate or purchase, maybe 50 products at most. But this is out of like, let's say, 100K products. So 50 over 100K is less than 0.1%, right? You guys agree? So this is where the 0.1% or 0.01% completion is coming from. So the matrix is only 0.1% or less complete, especially when you have a really large catalog and a customer can only purchase so many products, right? Or you can also look at Netflix, even in the context of Netflix. How many movies are there on Netflix? Any guesses? Any thought? Anyone? Let me ask someone. Nino, any thoughts?
I think it's like tons.
Okay. Okay. The literal definition of ton is 1,000 times something. Are you saying in thousands?
More than 1,000, I guess.
So
Oh, really?
Blake probably searched it up. So 3,700. Okay, great.
Nice.
So
Nice job.
Netflix is an interesting example. So I think, okay, so that's a good number. How many customers are there for Netflix? That's going to be a big number, right? So Netflix is like almost everyone we know has Netflix. So I think it's, yeah, it's in, getting towards 500,000, but yeah, maybe 200 million. So if you pick any of any of the movie at random, how many people would have actually watched it so far? Pick an average movie. Would it be 100 million? Probably not, right? So depending on the movie, you might have anywhere from 100,000 people that watched it to million to maybe 10 million, 20 million. So still, the ratio there is about 1%, right? So there's 1% missing entries. So again, depending on the data set, the number of missing entries in your data matrix changes. Like in the previous one we saw with customers and products, it's 0.1%, 0.01%, 0.1%. So here it's looking like 1%. But if you expand it from movies to TV shows and all the other documentaries that Netflix has, then that percentage is going to become even smaller, right? How many people have watched Close Encounters of the Third Kind, although it's a popular one, trending right now, but probably not, right? So it's trending right now, which means you haven't watched it yet. You might want to watch it. So yeah, so the percentage of, for that particular row or column of that matrix, you're going to have a lot of missing entries, right? So that's how, depending on the data set, you have more or less missing ratings. So whenever you have missing ratings and you still want to learn U and V, this is called the matrix factorization problem, matrix completion problem. And like, we should really understand why we want to learn the U and V once we, and how it helps us recommend, right? So that's very important to make sure we understand. So basically here you have your X and you have like a lot of missing ratings, missing entries, right? And you have a lot of questions because people haven't watched it or something. And then same thing goes for other rows and other columns as well, right? So if I want to predict this, let's say this is a question mark, I want to predict this. So I'm going to look at this row and then I'm going to look at this column. Okay. So when I do matrix factorization or matrix completion, I'm going to get factors for every single row and every single column, assuming there's at least one data point in every single row and every single column. If you had a row that had all question marks or a column that had all question marks, then there's no data to learn anything about that row or column. So you will not get a factor for that row or for that column, right? So here, the U is going to be, let's use the same encoding. Yeah, so let's use purple. I think purple is, yes. So this is U. and this is V. Okay, why is this U make sense? Well, if let's say this is let's say this is let's also give it some more dimension here. So this is customers, and then this is movies. Okay, since we're talking about movies, let's say this is the 100th customer, and then this is the 50th movie. Okay, so 50th movie and then 100 customer. So I'm going to be looking at the U100. So the 100th row of this matrix is going to correspond to the 100th customer, right? And then I'm going to look at the 50th V50, the 50th row of a column of this matrix. Okay, so what happens when I dot U100 with V50? What is this going to give me?
A scalar, is that supposed to be the prediction for the,
yeah, and what is yeah, and how do I interpret the scalar?
I don't understand.
I got something. I got some, let's say I got 0.5 or I got negative 0.3. So how am I going to interpret this? So the way U and V were learned is that whenever there's a 1 here, I want my U and V to dot and give me a 1, right? And whenever there's a 0, I want them to be orthogonal or, give me a low number, right? That's how I have set it up here. You're identifying factors U and V so that for every single rating that you want the UI and the VJ, the dot product, to be as close to the rating as possible. Okay, so that's how you're learning the U's and V's for every single row and every single column. So because you're learning it that way, if you get a U100.V50 that's high, this is high, that implies customer 100 likes movie 50, right? On the other hand, if this is low, it implies customer 100 may not like movie 50. Okay. Does that make sense? And because you're optimizing, so this is an optimization problem, right? So you're optimizing this function and it's an average. You're saying on an average for everything that I know in this matrix, like a customer has watched this movie. So if you maybe they watched it fully, so you're like, okay, they should get let's put a 1, and they haven't watched it, even like 5 minutes, let's put a 0. They didn't like it or whatever. You have some signal and you put a 0, and the others are question marks because I have no idea. So from all the 1s and 0s that kind of like learn the U's and V's so that you match it accordingly. So the U's and V's will be learned in such a way that as much as possible, they will try to optimize for what you know. And then for what you don't know, you can assume that whatever you're getting as a prediction is going to indicate whether they like it or they don't like it, because that's how you learned it, right? So that's like your test data. There's all these question marks for your test data. The training data is what you have, 0s and 1s, right? So, I mean, there's no like, I mean, you can say, okay, these are 2 different classes, 1s and 0s. You can also look at it that way. And then everything else that is a question mark is like in the test area. So we have no idea. And we are predicting there. So this is U100.V50 is actually giving us a prediction here. And you have to round it off, the prediction. Like you might get 0.8 or whatever, and then you have to make sure it falls in the right bucket. It's like 1 or 0 or whatever. So have a way of thresholding it and then putting it in the right category. Then you will be able to make a prediction. Does this customer like this movie or not? If they like the movie, then you recommend it. If they don't like the movie, don't recommend it. So matrix completion works on that principle. Learn these factors U and V, and then you can make it happen. Right. So let's go back to that, numbers that we had before again, right? So if you had like 100K customers, or we said 1 million customers. So 1 million customers. 100K products. But you only know, like, did we say, yeah, so 0.1%. So you only have 0.1% is also a lot because there are a lot of new products. So you only know 0.1% of this matrix. So 0.1% gives you 1 over 1,000. So wait, how much is this again? We said it was 100 billion, right? So 100 billion, yeah. So 0.1% of this matrix, this gives us 100 million training data points. And okay, so if this is 100 million training data points, what does the test data points size look like? Let's order.
Like order E to the 11 or something, or 10 to the 11.
It's still the same. It's order 100 billion.
Yeah.
You remove 100 million from 100 billion, it is still 100 billion. So, I mean, obviously, these are not exactly test data points because you may not have labels for them, but that's like, your test is going to be a subset of this because these are your unknowns. Like you really don't know if a customer likes this product or not. Like there's so many, there's like 100 billion things that you don't know, and there's 100 million things that you know, right? So let me also clarify the assumption here is you're assuming that one customer purchases 100 products or has purchased 100 products. And these products are distributed at random. So again, the rows and columns have that kind of symmetry, right? So that's the assumption, but that's a big assumption. And also I want to clarify, these are two different examples. So this is for movies and this is for products. But the same idea applies, right? And you can still do UV, you can still compute the U and V for the customer products matrix. So you're not going to fit it into a matrix because it's a huge matrix. It's going to go out of memory, but you're going to use the entries that you know, and then identify U and V for this, right? And we also said the U and V look really huge for this one as well. So U is this, and then V is this. U is what? It's 1 million by 1,000, right? And V is 1,000 by 100K. Yeah. So this tells us that the number of parameters equals 1 billion. So you have 100 billion unknowns, you have 100 million training data points, and you have 1 billion parameters. Okay, so let's write that down here. So this is 100 million train data points. 100 billion unknowns. And then 1 billion. This is all order, right? So let's make sure we understand this. Order 1 billion parameters. So is this underfitting, overfitting, or which scenario are you falling under? Or none of the above? Anyone? Under. So what is the definition of overfitting? Overfitting means you have more parameters than the number of data points that you have for training, right? Which overfitting always means you're trying to do too much when you don't have enough data. That's why the over means you're being over ambitious. So you need to like kind of tone things down or make things simpler. That's the message of overfitting. You're complicating things, and complication is usually because of the number of parameters. So in this case, we're actually overfitting, right? Because the number of parameters is, you know, it's much, it's greater than the number of data points. Or let me put it the other way around. Training data points is less than number of parameters. So 100 million is less than 1 billion, so you're overfitting. You're definitely not underfitting. So you're probably overfitting. I mean, it's not a huge overfitting, but yeah, it's still 1 billion versus 100 million. It's a factor of 10. Yeah, you might still be able to get away with it. But this is where, again, regularization can help in matrix factorization to make sure you're not overfitting. Is everyone familiar with overfitting? Like from a previous machine learning course, you must have looked at overfitting. Right? So we're not covering those concepts in this course. So if you've not looked into this much, I would suggest looking into overfitting and underfitting. And we will be looking at this in assignment 2 as well. So just kind of refresh your understanding of this. Okay. Any questions on these numbers and how we have computed them, and what it means and how does it connect to this? So I'm asking this again because I want you guys to be really clear. This is like the crux of this course. This is where you kind of you want to make sure you don't miss this out. Shouting, Ching, Nino, Blake, all good?
Yes.
Okay. All right. Ching, yeah. Ching was saying something. Okay.
Oh, no, I didn't.
Okay, cool. So again, this is a perfect segue for regularization. So when you're overfitting, so use regularization, right? Because regularization is saying don't over optimize on the data because there's not enough data and you have too many parameters. So you might be fitting too much to the training data without really understanding how the rest of the data looks like. So yeah, so this regularization by, this is Frobenius norm. We've looked at it in a previous assignment, right? It's just the sum of the squares of the entries of the matrix. So by minimizing this, you also make sure that none of the parameters in U or V are really bloated. So you're kind of keeping the weights down. So making sure you're not over-indexing on any set of customers or movies or products. Like you're kind of like saying, okay, I understand you're learning this in the U's and V's, but don't like, if I notice that you're going overboard, then I'm going to kind of regularize you, kind of keep you toned down. And that's what this regularizer is doing here. So this is supporting minimizing overfitting. So obviously here you see this lambda, right? So the lambda is something we call a hyperparameter. So again, just checking on the basics. So if lambda is high, do you overfit or underfit? Do you, okay, we're already overfitting. So if lambda is high, do you reduce overfitting or you're not reducing overfitting as much? So think about what happens. Lambda is here, you're minimizing over U and V, right? So when you have large lambda, what happens to U and V? Let's say lambda is infinity, right? You really, you said lambda to infinity. What's going to be U and V in that case? If lambda is infinity and you want to minimize this objective, the only way you will stay sane is by setting U and V to 0, right? If you don't set it to 0, then it'll all bloat up. It'll go to infinity. So you have to keep it. So U and V being 0 is like the simplest possible model you can have. For everything you predict 0. So that means you are actually reducing overfitting as you increase lambda. So that's a way to understand that as you increase lambda. So just go to the extreme. If you set lambda to be 0, you're back to square one, which means you're like having the overfitting that you had issues with before, it continues. So as lambda increases, you reduce overfitting further. So when lambda is tending to infinity, U and V enters the 0 matrix, right? And then if you set lambda equals 0, back to matrix completion. So does this make sense? Once you learn these U's and V's, how can you make prediction for any movie if a customer likes certain movie or a customer likes certain product, right? Just take those factors from the U. You have a customer factor, you have a movie factor, and then you just map it together. And in 2 dimensions, it's easy to visualize these things. In higher dimensions, it's harder. So in 2 dimensions, so let's say this is customers. Oh, sorry, that's not how we look at. Okay, these are your latent factors. So this is factor 1, factor 2. So let's say this is movie 1, this is movie 2, and then this is customer 2 and this is customer 1. So just by looking at this figure, would customer 1 like movie 2 or movie 1? More. Movie 2, right? And the reason is the dot product, the cosine between C1 and M2, the angle here is smaller. So that means the dot product is also higher. So what have we done here? We've taken the customer, the row of the C matrix. This is the C matrix. Let's say the C1, I think we want to use U here. This is U. And then this is so let's keep using U and V, right? So we used U and V. Okay, so C1 is going to be this. This is C1. And then M2 is this. again, we said U1, V2, right? But C1 means customer one, but when you look at the factor, it is the first row of this U matrix. If you look at movie 2, that's coming to the V factor. So that's the second column of the V matrix. So we are saying here that the dot product between the customer 1 and movie 2, this angle is smaller than customer 1 and movie 1, right? So this angle is, this is theta. This, let's say, some theta. This is a higher angle. So they are less similar. This is a smaller angle, so they're more similar. Similarly, would customer 2 like movie 1 more or movie 2 more? The same principle, right?
Yeah.
Movie 1. So again, okay, so let me ask you this question again. So that you clarify for yourself. So if I want to look at, okay. Oh, wow. What happened? I think my pencil ran out. Okay, so for customer 2 and movie 1, if you can write down what parts of U or V are we taking a dot product off, right? If you can just type in the chat, that'd be good. So for customer 2 and movie 1, like which row of U or which column of V are we looking at? Yeah, for C2 dot M1, yes. But see, C2 is representing customer 2, but the factor itself is coming from U. Yeah. So U2 dot V1. Does that make sense, right? So C2 represents customer 2, M1 represents movie 1, but the factors are where you're dotting it. So the factors are coming from U and V because the factors represent these customers in floats. So here we are able to see this in 2 dimensions because it's a 2-dimensional representation. That means U has only 2 dimensions. But if U was 1,000, like for example here, we were looking at 1 million by 1,000, you cannot visualize 1,000, right? But I just wanted to say that it's going to be something similar. In space, you're going to like map it out this way and say, oh, this is closer, this is farther. And that's how you're going to. The other thing is if you flip things, then the U might mean something else. So here we're looking at a customer by movies matrix or customer by products matrix. If you had products by customer matrix, what would you represent? It represent products, right? Because you flip the representation. So you have to understand how the matrix multiplication is happening to understand what each thing represents. So you have a matrix, there's a row, there's a column. The row means this, the column means this. Now, when I go to the factors, I have to carry along that representation for the data matrix to these factors as well and map it out correctly. And then I can use the appropriate rows and columns of U and V to take dot products and then make a recommendation. Does that make sense? Like it's possible to mix things up if you didn't map things out first in your head, right? That makes sense. Okay. I think we'll have to take a 5-minute Apple Pencil charging break. But feel free to ask any questions. We can go over questions as well while my Apple Pencil is charging.
I have a quick question.
Yeah.
Excuse me. If you change the rank in the SVD, so let's say you have like, 10 factors versus 100 factors, does that tend to like improve the prediction results because you have a higher like latent space kind of?
Yes, it does. It does.
Okay.
On the other hand, higher factors can also impact, so let's look at higher factors.
Like overfitting.
Yeah, because higher factors means more parameters, right?
Right.
So there's a trade-off. Like if you use only one factor, like there's no hardly any parameters, right? So you're not learning. But more factors, at some point you start overfitting. So again, the number of factors, there's a sweet spot. And that's why this formulation is good, because here what you would do is you would have a held out set of ratings that you don't use for training. And then you will adjust your lambda, validate on it to make sure you get the best error. So that's like the sweet spot where you're not overfitting or you're not underfitting.
Perfect. Thank you.
So there is a sweet spot on how many factors you want to pick, for sure. Okay, any other questions? Okay. Let me see where I'm with charge. Oh, that's strange, 40%. Okay. So either it's charging really quickly or there's some issue with the pencil. Okay. Yeah, do you guys need a break? Probably not, right? If you do, just let me know. Okay. So yeah, this understanding. So are we doing a break right now? Sorry, I was not sure. Okay, so let's get started. Hopefully we're all back from the break. Yeah, so you're asking about reduced rank. This is also called the reduced rank formulation, because this regularization is known to also reduce the dimensionality. Like some of the rows or columns may kind of like not become all zeros or in the process of regularization. So it is known to happen. So in addition to what you set as a fixed dimension of U and V, this regularization can also reduce it even further. So that's why it's called reduced rank formulation. Let's see. Yeah, I'll skip this. Skip to next lecture. Oh, yeah, something really weird about today. Not sure what's happening. Alternating minimization is not too complicated. The idea is that there are two sets of parameters. Wow. Is it because I'm having it backwards? Let's try this. Okay. Yeah, maybe I was on the sensitive side. No. No, the software is sensitive.
Are you charging right now? Charging your iPad?
I'm charging the iPad. Oh, is that why? Okay.
Yeah, because my iPad sometimes happens when I was charging.
Okay.
Yeah.
So Blake is mentioning that the pencil also has a cold. Yeah, maybe you're right. That's a good one. It's a good one. So the idea is two sets of parameters. Okay. So in our case, what are the two sets? There's U and then there is V, right? So let's put the U, let's put the U set here, then the V set here. So you fix V and then you optimize for U, and then you fix U and optimize for V. So it's kind of like a dance that's happening. You fix the U and then you go optimize V. Once you fix V, you go optimize U, and then you go back and forth. So that is the alternating optimization, right? How does it actually happen? Well, if you look at that formulation that we had there, minimize X minus UV we had something like this. So you fix u, that means I only minimize with respect to v. So maybe I fix u to u. Let's say you're in the 5th iteration, you already know what u is from before. So you say fix u to u phi, only optimize for v, right? So that means you've gone from here to here, right? So you fixed u to u phi, only optimize for v. Now you've learned a new v, let's call it v phi, fix v phi, and then learn u6. Fix u6, learn v6. Fix v6, learn u7, v7, u8, like that. So that's the alternating part. And this is a general technique when you have two sets of parameters in optimization. You can fix one, especially when they separate out. Like here, it multiplicatively separates out. So you can fix one and then optimize for the other. And that process is an algorithm, and it's known to converge to a local optima, right? So that's alternating minimization. So this is definitely one way to do matrix completion, but it's a little bit complicated because once you fix u and you want to optimize for v, do you exactly optimize? Do you have to again do gradient descent on this? That's all a little bit of a clunky thing. So there's like question marks on it, but in some scenarios you can probably do it. And people have done a lot of research on how you can keep simplify it further. Even I've also done research on this during my PhD days. But I just want to mention that this is one way of optimizing this matrix completion and matrix factorization formulation so that you can learn these factors u and v, right? So fix one, optimize the other, fix the other, optimize this one. So just keep going back and forth. Okay. But the more important one that I want to cover is, which we'll also look at in assignment 2, is stochastic gradient descent. So SGD stands for stochastic gradient descent. Everyone's heard about it? Yeah. Okay. So I just want to go through some of the basics of it. It'll be a refresher if you've already looked at it before, but also you'll be implementing SGD from scratch in your assignment 2 for recommender systems. So you'll be using an SGD based algorithm on a matrix completion problem with regularization and see how it does better on certain metrics as compared to SVD. So you see really, oh, by doing all of this, am I really getting a better result on what metrics and how? You can look at all of that in assignment 2. So underlying any engine behind machine learning training these days, look at Keras, PyTorch, scikit-learn, MXNet, any framework, deep learning, computer vision, natural language processing, there is stochastic gradient descent, or there is some variation of that, like AdaGrad, Adam, so there's like whatever variations of these things with momentum, without momentum, all of that. But basically there is stochastic gradient descent, some kind of stochastic gradient descent that's sitting in there. And it's kind of like, and not just stochastic gradient descent, it's mini batch. So many people use mini batch SGD, has become like a staple diet under the hood. So this is a nice pictorial understanding of how you have gradient descent, you have mini batch gradient descent, and stochastic gradient descent, right? So gradient descent is this blue thing, right? So kind of like goes smoothly from one place to the other. It can zigzag, but it's not going to, crazily zigzag. I mean, it's going to, it's. I mean, when you actually plot the, I think we'll have. Let's see, we have a graph for it. I think we used to have a graph for it. Okay. But anyway, I think you can also depict it here. So this is called the level sets. That means each of this ellipse is corresponds to the function value being a constant. So any point on this ellipse has the same function value. To reduce the function value, you have to go to the next ellipse, and then the next ellipse, and then the next ellipse. Does that make sense? So as you go inwards, your function value keeps reducing. And that's what you want to optimize. You want to optimize the function value, right? So that's how you're making progress. So if you plot the function value for gradient descent, it's going to be pretty much like smooth. So by smooth, I mean this. Doesn't mean that you will necessarily hit the optimal solution, but you might start to kind of converge somewhere, like for example, this is maybe the optimal is here, but it will take a long time to converge. But you can probably stop here and say, hey, I'm almost done. So that's what but this process is smooth. You see, there's no like up and down motions that's happening in gradient descent. And then this is stochastic gradient descent. So stochastic gradient descent looks really wild. Like, for example, you start here, you go into inner ellipse, and then you move out of the ellipse. Like in the fourth iteration, you've actually increased the loss function, right? See 1, so this is 1, 2, 3, and then 4. 4 is actually on an ellipse that's outside the one that 1 was on. So that means 4 has a higher loss function, right? So let's say this is, you start at U1, you go to U2, then you go to U3. Oh, U4, I'm actually doing worse. U4 has actually increased my loss function instead of reducing it. But that's how stochastic gradient descent works. It will increase it, but not by much, because on an average, you're going down. But you'll have all this randomness of going up and down a little bit. But eventually, it will zigzag a lot and finally reach this red dot. The red dot is like the nice sweet spot where you want to stop training and say, I'm done. And then mini batch. So yeah, so with, if you want to plot this, it's going to be like, so this is maybe SGD, kind of going crazy up and down and fluctuations and stuff. And then there is mini batch, which is kind of, there is some zigzags, but it's not like, it's not as crazy as SGD. So there are still some clings and bumps, but it's kind of going towards the optimum. So when you look at how the loss function changes for mini batch, it's going to be like this. So it's kind of fairly smooth. So this is mini batch SGD. Okay. This is loss. And this is number of iterations. So people have figured out. So then the question is, if gradient descent is nice and smooth, why do you want to use mini batch SGD? People use mini batch SGD. Maybe gradient descent takes fewer iterations than mini batch SGD. So why do you want to use mini batch SGD? Anyone?
Scalable, because your data could be too big, so you wouldn't be able to load it all at once.
Yeah. And also the per iteration complexity could be huge for, so usually when you compute gradient, so a lot of functions in machine learning are, they scale with the number of data points. So for each data point, you add it to the function or loss function, right? Because you're saying across all these data points, kind of make sure you get an average good fit, which means you're kind of averaging it. Average is summation and then divide. Summation means you're, you have, so when you compute the gradient, you're going to also have a summation, or you're going to have to include all these data points, right? And when you include all these data points, you're going to end up with a gradient, or the number of parameters is going to be significantly higher. And you're going to have to deal with cubic complexity and things like that. Whereas when you only look at a subset of the data points, then, or subset of the data points, then it's easy to compute the gradient. It's reduces number of computations. There's less storage involved. So the per iteration complexity is lower for stochastic gradient descent. But as you can see, stochastic gradient descent also takes a long time to converge. It can, oscillate a lot. It'll eventually converge will take a long time. So mini batch is that sweet spot where, yeah, the memory is not as high, but also it's not as slow as SGD in taking time to converge. So it's somewhere in between. So you have a good balance between speed and memory. So you have a good trade-off between the two. So that's why mini batch SGD is preferred. And you're looking at some set of data points at a time. Also, the difference between gradient descent, mini batch, and stochastic is mini batch and stochastic are stochastic. They have that randomness in which data points get picked. So with gradient descent, you learn from all data points in every iteration. You learn from all the data. But in stochastic gradient descent, you pick one data point at random and say, what do you have to teach me? I'll learn from you. And then you go to the next one and say, what do you have to teach me? And that's why if different data points are teaching different things, there is kind of like this random changes that's happening in SGD. But with mini batch, you say, let me pick a mini batch of 256 or 128. So that's, the hyperparameter you set in a library, 128, 256 mini batch. So then you say, oh, I will pick 256 of the data points at random. Then I'll go to the next 256 at random. Or you can also chop off the whole data set into sets of 256 and pick them at random. So you do a full pass. That's usually what it's done. You cover every single data point, but how you cover is random, because you can pick you can pick these 256 mini batches at random, right? And so the randomization is shown to help with machine learning. So it's not just a convenience of computation and memory. It also helps you do the task that you care about, which is learning, and not just optimization. So there is optimization, there is learning, there is speed, and there is memory. So all of these four are happening with mini batch gradient descent, right? So randomness also helps you not get stuck in local minima or bad local minima. So I think we'll look at this. Yeah. So I don't know, maybe this is, this is a good one, but this is not a good one, right? So I came down from here, I'm like here, but maybe I should have gone here, but I just got stuck here. So this could be a good local minima. And this is not so good. A good also in terms of learning. That means you've not learned enough, you're underfit. You're like converged too quickly. You didn't really optimize your parameters. Good local minima also in terms of learning, which means you're not overfitting, but you've learned enough, right? So that's what I mean, like good or not so good. So the randomness helps you. For example, if you did gradient descent, you might just go like that. If you did mini batch, you might be like, oh, let's just do some wandering. Oh, wait, there's something interesting here. Let's go here. But with gradient descent, you're like, oh, I'm very clear. I just go down this way and I'm done. But with stochastic, you are actually allowing for the randomness and the randomness in the data actually. So it's these dimensions are going to be the dimensions of the data. So you're picking which dimensions of the data which set of data points you are using to inform your gradient progression. Okay. I mean, there's a lot to go into gradient descent and mechanics of gradient descent. You can spend a whole course on just gradient descent. And I did one of them in my graduate school. So, but if you're interested, you can look it up. There's so many so many algorithms on it, but we don't need as much for recommender systems. So we just need to learn enough to be able to implement SGD or mini batch SGD for our purpose for recommender systems. Okay, so gradient descent, I think this is some fundamentals, like you take a convex or non-convex function, gradient descent allows you to find a local optima, right? So this is convex, this is concave, and this is non-convex. Is everyone clear? Like, I mean, there's also definitions of convexity in multiple dimensions. In 2 dimensions, you can visualize it this way. It's like a bowl, or it's like a hat. If it's a hat, it's concave. It's a bowl, it's convex. If it's something else like squiggly shape, it's non-convex. But in higher dimensions, there's like definitions, clear definitions of what convexity and concavity means. We'll not look into it, but these are good for, you can get a global optimum by gradient descent. You start, keep moving, converge. This is good for gradient ascent. You can ascend, get to the top. Here, depending on where you start, like I start, let's say I start, I start here, right? So that means I will probably, if I'm looking, I mean, I can go both ways, but let's say I'm tilted on this side, I'm going to converge here, right? If I start here, which side am I going to converge, left or right? So this is the axis. I'm picking points, in this dimension, right? For each point, there is a loss function that's given by this function value here. So if I pick a point somewhere here, which side am I going to converge, on the right or on the left? The purple one here. You can put in the chat, right? Yeah. So the way to look at it is to kind of look at it this way. So here, the negative gradient is pointing me this way. Negative gradient is high in this direction because the gradient is negative. So negative gradient is high in this direction. So you want to go in this direction, but once you hit here, you stop. So you converge here. And then if I'm somewhere here, then I'm like, oh, so the negative gradient is, I want to go in the direction of negative gradient. So gradient is always telling you the direction of ascent. Okay, the direction in which you will ascend. So the gradient will say this is the direction you want to go, but negative gradient will say go in this direction, right? So gradient descent is always going in negative gradient direction. So that's why the negative gradient is pointing you in this direction. So you're going to converge here. This point. Makes sense. So depending on where you start for a non-convex function, you can end up at different local optima. So that's why the starting point is important, but also the stochasticity helps you get to a better local optima, and the stochastic gradient descent and the mini batch stochastic gradient descent do better job with large data sets because they avoid some bad local minima. For example, this one, well, yeah, sure, you made progress, but not as much. This is doing better, I mean, you can have other ones in between and stuff. So that's the reason to the stochasticity also helps. Okay. Any questions on this? So that's the interesting thing. The gradient always points in the direction of ascent. So it's like if you go hiking and you say which way to the top, that's your gradient. Like this way to the top. Like, okay, that's your gradient because that's taking you upwards. But then it's a switchback. So you're starting to switch back. You say which way to the top, and there'll be opposite side, right? Because your kind of mountain's shape has changed, or your switchback is like telling you to go the other way. So, or even if it's a mountain and the mountain is like, right now, if you go this way, you're going to ascend. But once you get there, the ascent is this way. So that's why in gradient descent, you take steps. Because once you take a step, then okay, I think at that point, this was the direction to go, but right now it's changed. So let's pick a different direction. So that's why it happens in steps. Okay. All right, so that's gradient descent. Yeah, so like I said, negative gradient helps you direction descent. Gradient is ascent, so negative gradient is descent. If you want to minimize your loss function, you want to go in the direction of descent, which is negative gradient. So you always take a step in the direction of negative gradient. You take the gradient, take its negative, add it to your current point, and take a step. And that gives you the next. So that means if you had a U, let's say you had a U2, so then you would say U2 plus some step times negative gradient of your loss function at U2, V2. And then this gives me U3, right? It's very simple. Take your current U, take a step in the negative gradient of your loss function of all the parameters, but here we are fixing U, right? You can also optimize for U and V simultaneously, but here, let's say you fix your V, then you do this, and then this step also has to be chosen carefully, then you get your U3. So something like this is what you'll implement in assignment 2 with stochasticity and picking your data points carefully. Okay, so I think let's look at this this batch gradient descent. Oh, there's a lot to this. Yeah, maybe we should just cover it. Okay, so batch gradient descent is simple. The reason to cover batch gradient descent is to just understand, how gradient descent in general works. Is you always start with some initial point. Let's say you want to optimize a loss function, and W is your parameter. You initialize it to W0, maybe randomly, and then the step size is also called learning rate, right? And we probably all know this. So take a step in the negative gradient direction of the loss function at your previous parameter, and then update your parameter. And then keep repeating until you converge. So if you don't make any progress, then like your WK plus 1 is close to WK, then you haven't made any progress. So this is like saying this is your L of W, and this is W0, W1, so on, right? So as you change your W's, you're kind of converging. So here, maybe I'm at W19 and W20. So there's not much difference between the loss of W19 and W20. So stop. But at W0, I wouldn't stop because I'm making progress. So stop only when you're in this regime, right? And then you converge. So this is gradient descent in one direction. If you say you start here, this is negative gradient direction, keep taking steps, and then you converge here. So we covered this 2 dimensions. And the next is, there's a couple of other things. So yeah, like I mentioned, SGD is something that shows up in deep learning a lot. So gradient computations in deep learning is usually what we call backpropagation. So if you want to compute the gradient of the loss function in a deep learning architecture, that's backpropagation. That's how you compute it. And usually this is also based on auto differentiation. So in deep learning libraries, you don't have to worry about what does the gradient look like, how do I compose it, how do I compute it. Just mention which activation functions you're using, how many layers, what's your loss function look like, what's your target, what's your data, and then the framework will do auto differentiation for you using backpropagation. And then that gives you the gradient, and then that gradient gets used in mini batch gradient descent in deep learning, right? So I think this should also be familiar for most of you. So computing gradients, I think it's good to spend some amount of time on this, especially with assignment 2. So let's look at a simple function. So let's say we had a loss of, let's say we had a dot product function. So L of U is U transpose alpha. So what's the gradient of L with respect to U? Alpha is a constant vector. So let's say alpha is in 10 dimensions. U is also in 10 dimensions, right? So this would be alpha. You guys see this? In this case, it's not too complicated because you would say L of U is U1 alpha 1 plus U2 alpha 2 plus so on U10 alpha 10, right? This is true. So the gradient of L with respect to U let's say with respect to U1, is I only look at all the terms that have U1, which is only this one, and take the derivative with respect to U1. So this is d by du1 of U1 alpha 1, which is alpha 1, right? And then I do the same thing for, let's say, UK, I get alpha k. So that means if I put it all together, I get alpha 1, alpha 2, alpha 10, which is the same as alpha. So that means the gradient of L with respect to U is alpha. So gradient is just a collection of partial derivatives of all the parameters that you have in your model of the loss function. So take the loss function, take its partial derivative with respect to each parameter, and put it all together into a form of a vector or a matrix or whatever makes sense. And that result is the gradient. Yeah. So this is a simple example of how you would go from here to here. So this is called, how many of us have looked at ridge regularizer before in some previous course? Maybe we can do a quick exercise on this. Here's a poll link for it. This is a ridge regularization, which is like it's basically the L2 norm squared. And there's also a lambda function here. So it's lambda times the L2 norm square of W. So again, a reminder, L2 norm square of W is W1 squared plus W2 squared plus so on. Let's say there's D dimensions. W is in RD. So it's W2 squared. So this is what L2 norm square is. So again, using the same principle, if this is your loss function R, then what is the gradient with respect to W of R, right? The easy way of doing this is start by computing the derivative with respect to, let's say, W1 of R. And then, do it again for W2 and see if you find a pattern. And then your gradient is also going to be the same dimension as your parameter. So it's going to be in D dimensions. So see if you can get a D-dimensional vector that matches up with this pattern that you're seeing here. So let's take like a minute, a couple of minutes to look at this. And the poll link is here. Yeah, recording. Yeah, so the answer is C because again, go by first principles, right? So what happens when you take the derivative with respect to W1 of R? So that's derivative with respect to W1 of W1 squared plus W2 squared plus so on WD squared times lambda, right? So you have lambda as well. The only term that has W1 here is this. Everything else doesn't have. So you can just take the derivative with respect to W1, which is 2 W1, but then you also have lambda. So it's 2 lambda W1. And then if you look at W2, you get 2 lambda W2. So there's a pattern. It's 2 lambda something, 2 lambda WK. So 2 lambda comes out. So 2 lambda factors out, and then you get W1, W2, WD. But this is nothing but W, right? The vector W. So W1 is the individual entry. Actually, sometimes people use a thicker W here to denote vector. But then whatever, so you can say this is W. 2 lambda W is the vector. This is a entry or scalar. So it's 2 lambda W, right? Just see. Does that make sense? How we did that? Okay. Great. Okay, so yeah, I think so this is like, understanding gradients is important because it shows up in so many places. Gradient descent converges to a local minimum. If L is a convex function, all local minima is global minima. Wherever we start, gradient descent usually finds a local minima. And the learning rate that we mentioned in gradient descent algorithm is important. So smaller learning rate means it takes more time to converge. Larger learning rate, you can diverge. So this is like, so you can diverge. So it's not enough to go in the direction of negative gradient. It's also important to make sure that you are taking a reasonably small step, but not too small that you're not making progress. Too small, you're not making progress. Too large, you're diverging. Do you see? Like at this point, this is negative gradient, right? So negative gradient is going in this direction. But here, instead of taking a small step, I've taken such a huge step, right? I'm going from here to here. And then suddenly my loss is increased. At this point, negative gradient is this direction. Instead of taking a small step, I've taken a big step. Jump from here to here. That means this guy here. The same thing, I jump from here to here. So that, then you keep diverging. So that sometimes when you implement the stochastic gradient descent in your assignment, you're like, oh my God, I'm not converging. Then your learning rate is too high, right? Or the other scenario is I'm not making any progress. I'm not learning anything. Well, your learning rate is too low. So sometimes we have issues between too low or too high. So we covered gradient descent. Stochastic gradient descent is very similar. Let's say you have a loss function. Typically, you can break it down as a sum of individual loss functions, where each loss function has only one data point, right? So it's a summation over data points. So there are most loss functions in machine learning are of this kind, because you're averaging the error over multiple data points. So because you're averaging the error over multiple data points, you can always break up a loss function into sum of n loss functions, where n represents the number of data points, right? In such a scenario, you again initialize at random the weight vector. So for our case, right, we're looking at U and V. So U0, V0. So for matrix completion, you replace the W0 by U0, V0, right? You start with some matrix U and some matrix V at random. And then you pick a index I at random between 1 and n. And that means you're picking the data point at random. So you pick one of the data points, and then you take a step in the negative gradient of only that loss function that corresponds to that data point, right? Instead of looking at all data points, I only look at that data point. And that's why computing this gradient is easier, because you don't have to go through n data points. Let's say you had 1 billion data points. If you want to compute the gradient, it's billion times the cost of computing gradient for a single data point. So even though gradient descent will converge quickly in 100 steps, each of those 100 steps involves 1 billion computations, at least 1 billion computations. But in stochastic gradient descent, you just pick one data point and involves a computation of gradient computation with respect to one data point. And then you take a learning rate and a step in the direction of negative gradient, and then you update, and then you keep doing this until you converge. So this is the same as gradient descent. The difference comes here and here, right? So this is the difference. Okay. Then we saw this is how it looks like. And then mini batch. So mini batch, in mini batch, what we also do is we say let B be the number of batches and K be the batch size. So K is usually 256. And B is equal to n by 250, n by K, right? So the number of data points by the size of each batch is the number of batches, or the number of batches times the size of each batch is the number of data points, right? The math works out. So B is usually n by K, where K is the batch size. So again, initialize at random. Pick a batch of K data points. So let's say K is 256. You pick 256 data points at random between 1 and n. So call it y1 through ik. And now compute the gradient of all these data points, right? So you basically pool information from k data points. So for SGD, k equals 1, right? For mini batch, you have a k, which is 256 or whatever. And then compute the gradient summation, and then you multiply with the learning rate, right? It's actually good to normalize, because otherwise your learning rate will have to scale with n. So if you already normalized it here, like 1 by n or something, then that 1 by n shows up here. So then your learning rate doesn't have to scale with n. Otherwise, because this summation is going to start increasing and blowing up. So those things kind of also can help you quickly identify a suitable learning rate. And then you repeat step 2 and 3 until you converge, right? So like we saw before, this is batch gradient descent, this is mini batch gradient descent, some squiggliness, but you kind of start to converge, and you have a good trade-off between per iteration complexity and number of iterations. Okay, so this is kind of like a nice comparison. So let's say you look at data. Gradient descent is you use all data for each iteration. In mini batch SGD, you only use a mini batch, so 128 or 256 data points. So gradient descent is, in that sense, is good. It's learning from all of the data, but at a huge cost, like billion data points. Okay, so then you're going to have a billion, of order of billion complexity per iteration. And not to mention storing so many data points as well. So storage issues, computational issues. So that's why, you have to kind of be, that's why you kind of prefer mini batch. And then randomness, gradient descent is deterministic, but mini batch is stochastic. Error reduction is monotonic in gradient descent. It's stochastic here. Like, so this is the stochasticity. Stochastic. This is monotonic. Computation is high. Yes, computation is low. Memory can become intractable. I just cannot store a billion data points and keep computing gradients with respect to them, every single time. That's probably intractable. It's tractable because I only need to pick out certain data points at a time. So I don't need to store everything in memory. Convergence, yeah. So convergence here refers to, maybe not convergence, but let's call it stopping criteria. So stopping criteria for gradient descent is you're not making progress between the previous iteration and the next iteration. For mini batch SGD, especially if it's like a deep learning scenario, have you guys heard of this? Let's make a few passes over the data for deep learning. Let's do 2 passes, 3 passes, and then I still learned something really interesting. How many of us have seen this before? Yeah, because it takes a lot of time to train if you don't stop with 1 or 2 passes. But the idea of using passes is you're using all of the data. So pass means you've accounted for every single data point's contribution to the learning. And so you want to do at least 1 pass, but typically people do anywhere between 2 to 10 or 15 passes depending on the time, training time constraints that they have, and depending on the data set size. Sometimes the data set is so huge, you cannot even do 2 passes. You have to run through billions of data points. It takes a lot of, and you probably don't have that much time. Then you just do a couple of passes. So that's why passes gets used in deep learning, but in gradient descent, you look at relative error. Local minima traps. Yeah. Yeah, I think we covered this. The stochasticity helps with mini batch gradient descent, avoiding bad local minimum. So these are some pros and cons. Okay. Any questions so far on SGD, matrix factorization, matrix completion, making predictions from U's and V's, what U and V means? how do you learn UNV? How does it give us a recommendation? All of that.
One quick question.
Yeah.
In order to actually use SVD for good predictions, you have to have some sort of matrix completion that doesn't just fill in with, random data, right? Like if you were to fill in a matrix with like zeros, then you could run into a situation where you're not actually learning anything because it's just garbage.
For sure. SGD is more of true. So one is choosing a right approach to or modeling process. So you can say this is the right way to do it. So that's where we say, okay, don't just fill in and then compute UNV. So that's the approach. The second is once you pick an approach, what's the algorithm to actually train? So SGD is an algorithm to train for whichever, the right or the wrong approach. So you can, obviously, in the context of matrix completion, you want to use data that you know and not make assumptions of data that you don't know and still do SGD.
Gotcha.
Learn the factors UNV.
Okay, thank you.
Any other questions? Nino Ching shouting.
So far, so good.
Okay, great. So programming assignment 2, implement SGD yourself from scratch for recommender systems. Right? Apply it with or without regularizers. So again, overfitting or not. And we'll be looking at, assignment 2, obviously, movie lens data set. So 100K ratings. I think it's 100K ratings. But what's the size of the matrix? 10,000 users, 1,000 movies. I think there's many more. Yeah. So 100K ratings is actually severe undersampling. So there is a lot of unknowns. So I don't know, it's like 1% or 0.1% or something. But there's a lot of ratings missing in this data set. Yeah, and then you can do automatic differentiation. So I think this is it might be new for some of you, especially if you've not used it before, but implementing MXNet or PyTorch frameworks, auto differentiation, autograd to compute gradients automatically in your SGD module. So you're actually implementing the SGD from scratch. So that notebook that we'll have for assignment part 2 will have that aspect, right? And then you'll test that it's implemented right, and the training error will, obviously, if it's not going down, you've done something wrong. If it's going down, it makes sense, then you're in the right track. So obviously you can just plot the loss function versus number of iterations as you implement it and keep track that it's actually, so you want a curve like this. So if you see something like this is like, not in the right direction, and this is like, I want something like this. Okay, so loss number of iterations, or you can say passes or whatever, or batches, however you want to call this, passes, batches, number of batches. Okay, yeah, number of batches is makes sense for mini batches. Number of iterations for pure SGD. Yeah, so yeah, but a key thing is, in practice, no one ever implements SGD. It's like, it's all behind the hood. So, but this is you don't get to do this anywhere else. So I thought it'll be good to have it as part of the assignment. You don't get to do it outside of a course. There's always, people assume, oh yeah, SGD is in this library. SGD is in Keras, in PyTorch. So don't worry about it. So you never really get to maybe understand the intricacies of SGD until you implement it yourself. So, but here in the context of recommended systems, you get that nice peek into it. Cool. Anything else? Okay. So good luck with assignment 2. Hope everyone's got started on it. And I'll see you again on Wednesday. Okay. Also, yeah, another thing, project proposal will be due this Saturday. So the guidelines for it is, if I have not posted it already, I'll post it on Canvas. It's a one-pager that you want to submit. Actually, let me run it through right now. So, since we're all here on the call anyway, we'll just take a couple of minutes to run through it. Okay, so can everyone see this? So I'll post it on Canvas. You can take a look at this. So I would suggest you submit a project proposal. Like you can work in by yourself or in pairs, but not more than 2 people per project, so that you have a good amount of independence and focus on the project as well. And so I think we have from this weekend, I think we probably have 4 weeks, right, till the end of the quarter. So I believe quarter ends on 18th. I'm not exactly sure, but so yeah, let's say 15th or something is when we want to stop, or 16, 17. So that gives us about, I don't know, about 3.5 weeks, 3.5 to 4 weeks. So including the scoping the project proposal and everything. So that'll be 4 weeks, including project proposal scoping. So pick a project with a sufficient scope for 4 weeks. And I would suggest a few things like brainstorm ideas for a good project. So, within the scope of recommendation systems, right? So, and you can submit a one-pager as part of the proposal by this Saturday with your team member, or you want to do it by yourself, you can do it by yourself. So what's the project topic? What's the project goal? What specific interesting question are you looking to answer? What are some data sets you will probably use? Some methodologies like, okay, I want to use SVD, I want to use matrix factorization, I want to use maybe deep learning. What language will you code in? Let's say Python, or probably you have to use PyTorch for deep learning. What libraries and frameworks will you be using? Again, PyTorch or whatever, TensorFlow. Where would you ideally see this project be showcased? So this is also something that is up to you. Obviously, the more time you spend, the more you can even get to a conference paper if you spend enough time on a project. But at the very least, I would say getting a white paper, which is write a 10-page report, or 7 to 10-page report that looks like a proper conference paper, but it's a white paper. It's not something that's published, but it's pretty thorough. That would be minimum that we can expect. But if you have some place you want to show it as a poster, or you want to present, that can also be a goal that you can have. Or conferences will be really amazing, but that's something you can think about as well, what you want to do. I mean, there's like, it's all up to you, like but just definitely pick one of these and reference a few papers, maybe as you go through what topic you're looking at, and what, like, for example, I want to work on Twitter recommendations, or I want to look at YouTube recommendations. Look at some papers that have done something similar before, or maybe YouTube has a paper on how they do their recommendation systems, and you want to do some prototype version of that, right? That could be a project. Given a YouTube video, what are other videos that you would recommend, right? That's what YouTube is doing. It's just recommending all the videos, and we keep watching it, so it's doing a good job. So something like that. So what do you want to do? And the other thing is, what is something new you're contributing in this project that hasn't been explored before? It can be a really small thing, like I'm testing this algorithm on this data set, or this data set I'm trying to bring about something new. Something small is also completely fine, but it'll be nice to think about that as well. For the project proposal, just think of something ballpark, like something to begin with that you think, oh, this will be nice idea, this will be cool to explore, right? Something new, but it doesn't have to be concrete, because we'll have to see if it's new or not. Only as you read the papers, you'll understand if it's already done or not done, right? So that's one. And in terms of data sets, I would really encourage you to look into APIs like Twitter API, or Movie Lens. Anyway, we're looking at assignment 2. There's a lot of image data sets. If you want to look at Instagram, APIs help you to understand how you can get real data from public facing websites like Twitter. So the tweets are available through the API. If you get, you can apply for developer access, and once you have the developer access, you can extract public tweets and then use those to build your data set and make recommendations. Same thing with news. I mean, some areas maybe you have to download existing data sets, and that's fine. But there's like a whole bunch of things you can explore. Again, pick your area, whatever you feel. I want to work on recommendations in news or in Twitter, or whatever is exciting for you, you can pick that. And once you submit it on Saturday, we'll just review the project proposal. We'll have a one-on-one quick meeting to just make sure your proposal is set up for success, so that you can work on it in the next 4 weeks, right? And then so the due date is July 23rd. Shouldn't take too much long to work on the proposal. Maybe you have to spend half a day or something on this, but basically just think about a few things and then write up your one pager and then submit it. Any questions on this? Yeah. Nino Ching. Okay. So I'll upload this doc as well. So this is another something that's due this Saturday, but hopefully it doesn't. It's just like you just need to allocate some time for it. I'm doing it so that you have enough time for your project from next week. Okay, sounds good. All right, guys, that's about it for today, and see you on Wednesday.